Welcome back. Now, next type of filters, we are going to talk about scale spaces. But before I do that, I would like to do a little demonstration just to motivate why. Going back again to the notebook. These filters that we have been talking about until now, they will do something to the edges. They will do an overall filtering without taking any notice on what they filter. So now I want to look at what happens to edges, so sharp changes in the images when we apply a filter. And for that I have made some few steps. So first we create some test data. And the image is just this wedge. You can see there is a 1 pixel difference, 2 pixel difference, and so on up to 10 pixels difference. And we want to see what happens with this gap, because often when you try to do an analysis, you want to really be able to separate items that are close to each other and are detached. And as soon as you start applying a filter, the risk is that they start to grow together. And then you can lose relevant information. You can even do wrong simulations afterwards, because there is no possibility to put through information. So looking on to this one, we want to evaluate. We add noise at different strengths. We have, now I'm just using the uniform filter, and we observe what happens when we threshold this data. So the first run, I have a very high signal-to-noise ratio. I create some Gauss noise and add that to the image, and then I show it. Yeah, no big difference, except that it didn't change the color map. Now I apply a threshold. So the intensities in this image are 0 for black and 1 for white. And then I apply it on different cases. So I have the thresholded noisy image, no big difference. Then I start applying the filter. You can see here now that the edges are blurred, and it's getting more and more blurred. Actually, oh, I can't show that so well. That does it? Yep. Sorry that you can't see the text maybe up in this part, but and then I try to segment it, and the first difference you can see is that this bridge here has been made, and it's even more and more depending on the filter kernel size. I can put it up. So you see that there is an effect between filtering and segmentation for performance afterwards. Now, if I would add some more noise to it, so I make it something like that, no, like that. So now it's getting really noisy. And when I apply it, first of all, thresholding, now you start seeing that there are a lot of misclassified pixels. Well, the gap is still there, but you have a lot of misguiding information. So then we apply the filter. You can see the effect of the filter is that you smooth out all the noise, and here it's pretty well smooth. But still, you have the problem with the bridge here, that it bridges, well, a few misclassified pixels you get, but not as much as up here. And that is the reason, or the motivation, to go into a different kind of filter techniques, which are these scale space based filters. Let's move over to lecture slides again. And first of all, we have our previous filters. They can not cope so well with edges. The other thing is, if we have texture noise, it may be that it can be misinterpreted into being features in the image. And the basic idea of working with scale spaces is that It's weak. Okay. So down here, you have the full scale, and then you just downsample, making the images smaller. That means you take out the relevance of small features, and then you scale it up to some level where you still can see the relevant features, but not kill them completely. And the idea is that you can do actually filtering on different levels to gain a better filter performance. And the first thing to go on is the wavelets. It's actually doing this scaling, but it's doing it in a smart way, so you can actually extract a trend and a detail image from each transform step. So you can do the first part here, you have the original image, which you divide into a trend and detail. Then you take the wavelet transform of the trend to come to the next level, and with that you shrink the images all the time, but you still maintain all the information needed to go back again, because this is possible to invert. And you can use it for noise reduction, you can use it for analysis, you can use it for segmentation. Compression is a popular topic because all our different movie compressors and picture compressors are using wavelets or wavelets-like ideas for the reduction. So looking at one-dimensional signal first. So here I have the a sine and a step. And I add on that, add some noise. And when you do the first decomposition, you can see that, okay, a little bit less noise maybe, and it's also compacted, and here you have details, so that would be all the rapid changes. Then you do it the next, you take this one, go in here, and then you start seeing actually it's almost a sine curve and still a lot of noise on top. And decompose that one again, then you start seeing, oh, well, it's almost a sine, and it's almost a step, and still a lot of noise on top. So this is what's being used for the filtering and compression, that you can work on these levels. So you can say that everything that goes over some level, which I'm going to show on the next slide or next slides. So that was it, 1D case. Now we have a 2D case. Now we not only have the trend, but we also have different directions that we look at. So this is looking in the vertical direction, this is looking in the horizontal direction, and this is diagonal information. And when we do the decomposition, now we take the whole image, get the trend, vertical, horizontal, diagonal, take the trend, make the same block again, and that is the procedure that you do a couple of times. How many times depends on what you want to achieve and what you can allow yourself to do. And we'll see some example on the real data. Not noisy right now, but you can see here now you have this input image, and the big ones are the detail images on scale 1, detail images scale 2, detail images scale 3, and the trend. The trend doesn't need to be saved between the steps, so that one is only on the fully reduced scale. And here you can also see again, here you have horizontal information. Well, it's a bit hard to see the diagonal, but you start seeing them in these two. Here you have the vertical information. And looking now at using this for noise reduction, then you have the signal that you want to decompose in 1 or 2 levels. Now I only did 1. So I have the trend here, I have the detail, and then I say all signals that are within this band of a threshold, they are considered to be noise. Everything that peaks out must be some relevant information in the image. And then we just clean the rest, set it to 0. and keep only those peaks. And the next step is we get this image or this detail, combine it with the trend, and afterwards we get the filtered image like that. So you can see that the frequency component of the noise here has been filtered. And that is the effect that we want to look at. And here's an example. And so this is an original image, pretty noisy. I apply, there are a huge catalog of different wavelet bases, the ways of transforming. And they have some characteristic features, they have different sizes to make them sensitive to different characteristics of the images. Some wavelet bases are ideal for compression, other ones are better for noise reduction. And here I use a very simple one. Simlet 2 is in principle just -1, 1, and so it's just a single two-piece wavelet. Very simple base, but that one already can help us with 2 levels of decomposition to come from this one to this one. And if you look at your slides on the screen, you can see that there are some artifacts in it, and that is where maybe the thresholding got a little bit confused. Maybe it was an outlier that was interpreted as structure, and that gives some ripple effects. And you probably have seen this ripple effect also in JPEG, hard compressed JPEG images, that there are small ripplets a little bit all over the image. And that is due to this misinterpretation effect. So that is an artifact that you don't want to see, but it comes with the wavelet filtering if you don't watch out. And here you can see the histogram. Before filtering, after filtering. And you can see that, for example, these structures, they're pretty well maintained still. And the filter effect is pretty strong. So, leaving the wavelets now, going over to a different kind of filters. And now we are about to describe scale spaces with help of partial differential equations. And again, we have an original image, which is noisy. And with help of these filters, you can get to this, or even to that. And I'm going to show you these 2 filters in detail soon. And the purpose of these filters, they are very well at preserving edges. So you can see here, for example, these edges, they're pretty sharp still. And getting it that sharp with so strong filter effect is not possible with convolution filters. Also not median filters wouldn't do it. But maybe you may think this is maybe a little bit too smooth. Here is another alternative which has a little bit more edge roughness maintained. But again, it's a question of what you want to achieve with the filtering, how hard you can go with this filtering. And looking into the diffusion filter, so going to the start point, this filter is inspired by the heat transport equation. So you have temperature and you have some diffusion coefficient, and then you can actually, in the end, you say that the image to filter is corresponding to the temperature that you want to let transfer. But when you apply this equation to this image, you can see here the effect of it. After a few iterations, it turns into nothing. So it will homogenize into a constant level, which is the nature of temperature transport or heat transport. So it will sooner or later homogenize. So we need to do something to prevent the diffusion to go further, and that is to control the diffusivity. And we want the diffusivity to be 0, close to edges, and to be 1 in flat regions. And for that, they have come up with an equation, a threshold equation that essentially controls this for us. There's a few parameters that you can play with, but the sensitivity can be controlled to be more or less steep depending on how strong you want to filter. And then afterwards, we can get a revised equation looking like this. So this is the new diffusivity. And the edges of the image now, the diffusivity of this image now turns into this, where you can see that it's very much white, which is full diffusion, and black, which is stop. So it will only diffuse within these controlled regions. And then you have a much better effect. But the problem again, the gradient here, absolute gradient, is very noise sensitive. That was actually, the purpose of it is to detect rapid changes, which includes the noise. So we need to do something more. And that something more is actually to smooth the gradient once you have done it. And that gives us more safe information about where the edges are. And here again, we see the same example. And you can see the filter effect is improving. So you see the filter steps. You may see it better on your own screen, possibly. But it's doing a pretty good job now. Then people were not happy with the performance of these filters. They have some drawbacks. They may be a little bit not smoothing as good enough, or they have some problems around some edges, etc. So then they come up to total variation minimization frameworks, where you have a noise term and fidelity term, and they are regularized to each other to produce a much better filtering effect. And what we are normalizing to is the total variation of the image, which you see down here. And with that, so the fidelity is essentially original minus filtered. And the idea is essentially that the diffusion filters, they came from small scales, making them greater and greater. This new framework turned it upside down, because usually you want the big features and add smaller features. So the new filter techniques, they actually go from that direction. So they look at the large features and then add more and more fine details until you have reached the good information. And one of them is the inverse gate space filter here in the ROF model, which I've been using a lot in our different experiments. And the equation for it turns out like this. It's not too hard to implement, actually. Where you have F is the input image, and U is the filtered image, and then you have this support variable V, which can add on to the regularization of the data. And looking at what happens when you apply this filter is you have this noisy image, and in relative few iterations you can come into very strong filter effect. Now it can be discussed how far we want to go, because some features, they will actually be smoothed out. So in the end you will only have the greatest features. But this one has helped us, for example, getting from a single histogram mode, so all gray levels is just one big undistinguishable blob, and afterwards we were able to segment 7 different classes applying this kind of filter. So it's very powerful, and if you want to play with it, I can give you some hints afterwards where to get some code to play with. And iterations, they actually have an interesting path. So in the beginning, you start filtering and you improve and improve. Also, actually, you denoise more and more. And at some certain point, you're actually going back to the original. So when you tune this filter, you should usually work in the region around here. That gives you the best filter effect. And another one which came a little bit later is the non-local smoothing. And that's a very interesting approach. So it's actually computing the average, computing the average in a global sense. So every pixel is averaged together with all the other pixels which have similar neighborhoods. And that makes it very powerful. You can do a very good filtering effect with this kind of filter. And what you have is a filter that is really hard to compute because it's n squared in the complexity. So doing three-dimensional images takes ages to do, because you have to compare every pixel with all the other pixels and then weight them together. And that makes it very time-consuming. Now there are schemes that look more locally, and then you can speed it up a lot. So this weighting factor here is actually the sum of all pixels, and that's the time-consuming part. And then you have to also compute the weights on local neighborhoods. But the filter effect is very attractive. You can really extract very good the noise from the original information. This is only done in 2D. That's why you still see the ring artifacts, but ring artifacts usually appear only on single slices. So if I would have done this in 3D, probably the rings would have also disappeared. This filter is available in Scikit image package, so you can actually play with it yourself. It's not in the exercises, but I would recommend that you actually, there's one exercise about using wavelets. I would recommend that you look at the non-local means instead of the wavelets. So in general, it has a very good smoothing effects, strong thin lines, so very sharp edges. They are nicely preserved. And there could be some patchiness that you could get also, which is maybe an unwanted feature. So the complexity, as I mentioned, is n to the squared. I did some very primitive implementation and realized that if I would do something larger than 100 by 100 pixels, I would probably sit for astronomical times. For example, 1,000 by 1,000 by 1,000, forget it. So you really need to do a smart implementation for it. And then actually the thing I said before, that you can reduce the focus area, and with that you can improve the speed a lot. Last part is verifying what you have done. So you have done a lot of filtering, and my former boss, he coined the term data massage. You massage the data until it gets into what you want it to be. So that should be avoided. You should, of course, filter as much as you need to get the right information, but don't overdo it, because then you may actually invent new things. And there are different ways of doing this inspection. One is just plainly visual inspection. The eye is pretty good, actually, to see, am I doing something that makes sense? If the eye tells you this doesn't make sense, then it's time to reevaluate. Then you can look at difference images, and you can really do a heavy evaluation procedure. So looking at, first of all, difference images. If you have a noisy image and apply a filter to it and you get that, then you should be very happy, because then you have an ideal filter. It takes out the noise and saves all the relevant structure. Then you could actually do some over-smoothing, which would happen if you were to apply, for example, a convolution filter. Then you would get effects like this, where you see that the edges, they are still remaining, And that is usually the case that you have to look for, that you don't have any relevant edges in the difference image. A bad one is intensity scaling, so you actually modify the intensity. And in some cases you can even have a geometric shift. Many of these filters work on differential schemes, so it may happen that you shift your image by 1 or 2 pixels, and that shouldn't happen, because then you're not comparable to the original. So the difference is a very strong tool for doing this verification. And the other one would be to take the long route, that is to do a smoke test, provoke your filter system until it fails. And the smoke test in principle came from electronics, the term that you actually boost in some high power to your electronics, and the component that gets hot is the one you should avoid. So then you know where it is. What we do in reality is scan the different parameter settings for different signal-to-noise ratio. So that is our setup. So what we have to do is, first of all, create some phantom image with relevant features. It doesn't help if you have just boxes and circles. If you have some complex anatomical structure, or what do I know, a porous medium, then boxes and spheres don't help you. Then you add some noise of different signal-to-noise ratio. You could even also apply some blurring that would correspond to the optical transfer functions of the acquisition, and then apply the noise. And then you apply the processing methods, scanning the parameter space. So some filters have 2 or 3 different parameters that you need to tune. And then you start measuring the difference or with different metrics. And then you repeat these steps several times to get better statistics. And finally, you have to plot the results and see where you have the breakdown points and what's going to happen in the images. Different metrics that we use would be, one is the mean squared error. You have the ground truth, you know what you had in the beginning as you created a phantom, and then subtract it and square the difference from what you have processed. So this is a very common use, it's easy to compute. Then we have a little bit more complex metric, which is a structural similarity. Starts looking at different features and also how well does it look like, actually. So this was defined for video transmission check. Does the transfer data look like what we sent in the beginning? And this is a little bit stronger index, and I would say it's good to have a combination of the two. The authors of that paper, they say, forget the mean squared error, but I think a combination is good to have as a comparison between the two methods. And here I have an example, what I did many years ago, where I create a structure. So this was a segmentation method to identify roots in soil. So I created some root-like structures. So it's more fractal structure with branches, and did that with different sizes. And then I added noise at different levels, and then I started processing and could see the result when the method broke down and how well it behaved under different noise levels. So you can see that there is a clear, under some conditions, there are clear breakdown points where it fails to work at all. I think it was that the root system was disconnected, and then there was nothing to work on. So, then I could also identify where is our working point, and I think we were about somewhere around here, or even in this one without the black one. So it was okay for our processing case. And now we come to a little summary. We have now looked at very many filters. We have convolution filters, we have median filters, wavelet filtering, diffusion filtering, and inverse case phase filtering. And applying those filters to different signal-to-noise ratios. So this is the original. On this level, you don't see a difference. Then you add a little bit more, some noise, add more noise, and add really much noise. And you can see how the different filters behave. The convolution and median filters down here, they still have a lot of noise effects in them. But if you come to those two filter types, then we start getting pretty nice results still. These are just plain geometric structures, so it's, of course, a very synthetic case, but still it demonstrates a little bit what it looks like. And now for the next slide, I focus on the little area here around the middle cross, and to see what happens with these different filters, how they behave. The box filter introduces a lot of blurring. The median filter cuts off the corners from the cross. The wavelet filter does pretty good until we come down here somewhere. Then it's starting to fade pretty much. The diffusion filter, due to the implementation around the edges, we have now this edge barrier, and I must admit there are better implementations of the diffusion filter, which actually also look along the edges and filter them too. But in this case, I had one that didn't take care about that. And you can see really the effect that the edges, they are noisy, but the rest is pretty well smooth. And then coming to the last one with the ISS filter is the one that has the strongest filter effect and still maintain the structures relatively good if you compare to the other ones under the same condition. So that is the overview of the different filters, and the final take-home message. There are, depending on how noisy and the character of your data, there are many approaches. Can also be how much time you have. I mean, the convolution and median filters, they are pretty quick filters, whereas the PDE filters, it takes some time to execute. Some years ago, we did a really heavy filtering. It took, at that time on that computer, more than 1 day to filter. Nowadays, we can do it a lot faster, but still, it takes a long time to solve these filters. So it's a little bit what you need and how big sledgehammer you need to take in. So which one you choose is, of course, purpose of the data, quality requirements, available time. Sometimes it's actually enough to do quick and dirty, just give it a convolution and you get the first idea, but it may not be sufficient for them for the final analysis. And in principle, any good measurement, take the time to do a good measurement, is better than applying a lot of filter techniques. But in the case that you would have bad data, there are also techniques that can help you to get along with that. And that brings me to exercise links. So I don't know how much you have set up already last week, but I believe you have your accounts here. Is that true? If you want to do the exercises on your own computer, you can download an Anaconda environment, which is linked here if you just hover on Anaconda. And then there are some instructions how to install Python on your accounts here. Then there are some exercises that you can play with during the next hour. Now I have some minutes left, so any questions before we take a break and continue with the rest? No? Everything clear?